Hi, welcome to StatStuff. I'm Matt Hansen. In the previous lesson I talked about normal distributions. So in this lesson I'll cover non-normal distributions and how you can test those also using a normality test. So let's begin by defining what we mean by a non-normal distribution.
Well, a non-normal distribution means that there's some sort of bias or skewness in the data itself. Now, since normal distributions reflect a natural randomness that occurs in life, then we would say a non-normal distribution represents things that are not random, or there's something that's influencing its results, and we just have something that doesn't reflect that natural randomness, so it's causing this non-normal expectation in the representation in the data and how it's distributed. So the bias that we have in the data can be caused by two possible things. It's either in the method that we used in gathering the sample data. Maybe that method itself was not random and it caused us to collect the data that doesn't really represent the population and therefore is not normal. Or it could be the process itself, that is where we're collecting our data from. Maybe the process itself has something that's skewing it, so even though we could have been completely random in our method for collecting the data, the process itself, if it's non-normal in the way the process is set up, it could have influenced the collection of the data that we had from that process. So let's go through an example. Let's say that we're trying to measure the life of 1,000 batteries that we collected, and we might expect that the life of each battery represents maybe 50 hours each on the average. Well, what kind of distribution would you expect to see? Well, let's say for 1,000 batteries, we might expect it to be a normal distribution. If we expect each battery to, say, be operating at about 50 hours in length of time, we wouldn't expect every one of them to be exactly 50. But we might expect some of them to be around 50, or the majority around 50. There might be some a little bit more and some a little bit less, but somewhere hovering around whatever that expectation is. But if it's not normal in our distribution, then what could be some of the things that are causing it? Well, again, I would first look at maybe the method and how we collected the data. If we saw that it was non-normal in the sense that it wasn't just around 50, but maybe we saw a large portion that were actually only about 30 hours in the length of time, and then there might have been some still around 50 and maybe having a right tail going off where there's an extended period of time that for the life of the battery, but the majority, the central part, tends to be much less than what we expected. Again, looking like a non-normal distribution. Well, again, in that case, it could be several things, and we'd first probably want to look at how we collected our data. Did we really collect it in a random format, or is it actually something in the process itself? Maybe we didn't get a fair representation across the different plants where the batteries were being produced, or maybe we didn't get a fair representation of the proportions of batteries that were made. Maybe we have a larger portion of AA's that are made compared to C or D batteries, but in our sample that we collected we have the opposite. Maybe we have more of these C or D batteries than the AA's. Again, that would indicate that we may have not collected it in a normal representation, and therefore it would create a non-normal distribution in our data. So if there's some things like that we find, then how is it that we can make that into a normal distribution? Well, if it is a problem in how we've collected the data, then we would have to go back and figure out how we can make sure we're getting a fair representation, again, in a random collection of those batteries we might want to use for our testing. And we would also just want to make sure we account for all those other things that could be influencing it as well, making sure that we're not wrongly influencing the data collection. And that way, if there is still something that's non-normal in our distribution, it could be indicative of something that is wrong, maybe some sort of root cause, and that we need to fix. Now, the measurement for central tendency when we're using a non-normal distribution would be the median. It would not be the average like we typically would use in a normal distribution. The reason is because when you have a non-normal distribution, that bias that's in the data will cause the mean or the average to shift. So if our central tendency tends to be shifted more to the left-hand side, then that means our mean is going to shift toward the left-hand side, or the opposite. If it happens to shift toward the right, then our mean is going to be shifting. And because of that, now where the shift is occurring, it doesn't truly represent the midpoint or that central tendency like we would expect when it's a non-normal distribution like that. However, the median, which is at the 50th percentile, that will never shift. The 50th percentile is always going to be the 50th percentile, no matter whether it's a normal or non-normal distribution. So if we've got a non-normal distribution, that might look like this. We have data points, more of it being on the left-hand side and fewer on the right-hand side. Now you can ignore the blue line. The blue line is basically Minitab's version of trying to fit a bell curve in there, and if you can tell that it's not having a very good job at successfully fitting the bell curve in there, because we have more data points on the left hand side where there's that shift, and it looks like a non-normal data set. Well, the way we might plot it out in a logarithmic scale, if we're doing a normality plot like this to test for it, we might look skewed like this, where the red data points that are plotted on here are no longer in a line. They're kind of shifting like this. And if you held a fat pencil across this, like we might have done in a normality test for a normal distribution, some of those red dots would fall outside of that. And because of that, and it's not falling on a straight line, and because of this test itself, the Anderson-Darling test, where it's showing the p-value is less than 0.05, which might be our alpha risk, because of that, we might say this is a non-normal distribution. And if it is non-normal distribution, then we would concur we'd have to use the median as our measurement for central tendency. So what type of non-normal distribution is it? Sometimes, depending on the test we use, we need to figure out what type of non-normal distribution our data might represent. There's several that it could be. It could be a y-able distribution, or log normal, or gamma, or logistic, or something different like that. If you want to figure out which form of non-normal distribution you have, if it's pertinent to the test you're using, there is a way to kind of figure that out if you have Minitab. Now, this is not available in the student version of Minitab 14 that's available out there. It's more in the full version that's available. So if you have a full version of Minitab, then you can follow through the menu to Stat, then Reliability/Survival, then Distribution Analysis Right, and then Distribution ID Plot. Using that particular tool, then when you plug that in, you'll be able to figure out from there, based off of the one that has the highest correlation coefficient, that will tell you the type of non-normal distribution you probably have. Again, if you're doing some tests that require knowing the type of non-normal distribution, this is one method you can use to figure it out. But sometimes when you're not sure, sometimes if it's a non-normal distribution, I would tend to just refer to it as a y-able distribution, which tends to be most of the ones that I've seen in the business area where I've worked.
Now let's talk about something peculiar that sometimes occurs in our data. It's called a bimodal distribution.
Well, a bimodal distribution occurs when it appears that there's two central tendencies, or maybe like at least two bell curves that are occurring within data. It is possible to have more than one bell curve, or what's called multimodality, but it's not very common that occurs. And we say multimodality or bimodal. We're getting that name simply because the word mode, from a statistical standpoint, refers to the frequency of, or what is the most frequent value within a data set. And when you say bimodal, bi meaning two, you're basically saying you almost have like two modes. You have two values that are very frequent, or most frequent within your data set. Or again, it could be more than two. It doesn't have to be just two when we call it a bimodal distribution. It could be sometimes 3 or 4, or what we refer to then as multimodality. But again, it's not very common that occurs, but when they occur, they're usually occurring because your observations are actually coming from different populations. So most likely the things that are causing this are because you might have more than one population that's representing your data, but you've gathered it all together and kind of jumbled it together where they have different central tendencies, so they're kind of overlaying together on top of each other. So it's important when you see something like that to clearly try to figure out what's causing this, and to make sure that you don't analyze your data in that format, but that you appropriately separate your data so that you're analyzing it in the proper representation it should have. That is, it's representing the proper population as intended. Now, here's an example of what one might look like. And this is based off of the graphical summary that can be created from Minitab. So in this example, we can see the distribution here shown through this histogram. You can see that there's two peaks that are occurring in the data set. And from what it looks like there's probably two different populations, or two different distributions that are overlaying one another. So what are some of the things that we can conclude from this result? Well, it looks like, according to this, if we were to look at the mean, 39.75, and the median at 40, well, those are almost identical to one another. So according to this, the mean and the median are about the same, which is a characteristic we expect for a normal distribution. And according to this, the mean and the median falls right here, but that's the lowest point. So it's very odd that even though the mean and median look like they might be very close to each other, and it might be representative of a normal distribution, looking at the data, that obviously is not the central tendency. It seems like there's different central tendencies than where it's showing it is in this data set. So something's obviously going wrong. So according to this, we might ask, is this a normal or non-normal distribution? Well, it looks obviously like it's not normal. But again, if we want to confirm it, we would go to the Anderson-Darling normality test, and this would confirm for us that the p-value is less than 0.05 if that's our alpha risk. So in that case, we would say it's a non-normal distribution. So what about the central tendency? Is it reliable? Well, again, if we're looking at 39.75 and 40 as either of these methods for central tendency, we cannot trust it because it's obviously not representing the central tendency for this particular distribution. So how is it that we might be able to fix this? Well, we'd have to go into the data and figure out what is causing these two separate groups to represent these two separate populations in here. It might be represented by different locations or represented by different parts or equipment that's being represented, and maybe we didn't realize that we've got them jumbled together. So whatever it is, we need to figure out how we'd split these into the appropriate groups, then we'd extend our analysis only to represent each group individually and analyze them separately rather than together like this.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
Well, if you have any time, I'd like you to just open up the sample data file that's been provided on the website, and then with that data, run the normality test on each of those continuous metric values represented within the data. Then ask yourself which of the metrics are non-normally distributed, and how is it that you can prove they're non-normal, and which metric, if any, has multimodality. Which of those is bimodal, or it seems to have more than one distribution represented within it, more than one population. Now, after doing that, what I'd like you to try to do is look at your own data that you have within your organization. See if you could pull some historical data for at least 2 different continuous metrics in your organization, and try to run the same things here again, where you run a normality test for each one, and then you find out which ones might be non-normally distributed and how you can prove they're non-normally distributed. Or do you see any that might have multimodality?
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hansen. Thanks for watching.